All right, good morning, everyone. Hello, everyone. All right, I guess we're all probably complaining about Lab 1. Okay, so any questions from the previous lecture where we learned to create processes and had a lot of fun with it? Right? Okay, nothing. All right, great, because we're going to get into more of it today. So again, just in the recap, just to make it crystal clear, because the other section didn't like what fork returned. So how processes work is they're assigned a process ID, or PID, right? People just call them PID because we just like to take shortcuts. As soon as it gets created, so that's assigned by the operating system, and it doesn't change as long as that process is alive. And remember, a process is just an execution of your program, so it's actually running. And all the process ID is just a number, and it's unique for every active process, so it won't change out from under you. So if you create a process, it will keep that process ID until it is terminated, and we're going to see how to actually remove it today, because if you just call exit, that doesn't necessarily mean your process dies, and we'll see what that means today. But on most Linux systems, it's just a number, right? So it has some maximum. For some reason, the maximum is like 32,000, and then 0 is reserved as like an invalid number, or just an invalid number to signal a return value. And then eventually, right, you're going to probably run out of numbers if you never reboot your computer. So the Linux kernel will recycle a process ID, right? So if I'm process ID 1000, I die, then I'm no longer running, so process ID 1000 is no longer in use. So if a new process starts, the kernel could assign it process ID 1000. And remember, the kind of unique thing about processes are, just to give it a name, is they have their own address space. And what an address space is just their view of memory, right? It's an independent view of memory. One process doesn't affect another process. So we saw as soon as we cloned it, or as soon as we forked it, we got two processes that looked exactly the same down to their memory addresses and what their values were. And then if we changed anything, right, the processes didn't affect another one. So any questions on that, which is kind of what we did yesterday? Right. Okay. So just to illustrate it super clear with that process diagram, so this is how you would run some processes even on a single core. So assume we only have a single CPU, single core, so we can only run one process at a time. So Firefox, something would launch Firefox. For now, we don't care. It would get assigned a process ID, in this case 1337. And it would start in this created state where the kernel would have to load it into memory and set everything up, initialize the program counter and all that stuff. So then as soon as it's able to execute, it goes into this waiting state where we could actually run it if the kernel decided to schedule it to run, right? And we haven't talked about schedulers yet. We just talked about the actual mechanics of switching over a process. So if I want to switch this process from waiting to running, what do I have to do? Anyone tell me the process I have to do or what it's called? Yep. Yeah, so I have to context switch, right? Something else is probably running right now, some other process, maybe the kernel. So I have to context switch and make this process running. So at the very minimum, I have to, put whatever is currently running to, retire whatever is currently running, save its current registers, at least its program counter, then store that somewhere. Then I'm going to reload the program counter for this, which would be initialized to whatever the entry point is, and then I can go ahead and run it. So say it's going, it's running, and then we create a tab. Just the architecture of Firefox or Chrome, whatever web browser is, they will spawn a new process for every tab just to get that nice isolation. So if one tab dies, the main browser doesn't die. So as soon as this happens, right, it creates a tab. If it creates a new process, anyone want to tell me what system call it has to use to create a new process? Fork, right? So we're going to fork. So the kernel needs to handle the fork. It might just put this in a waiting state and execute all the fork code, because in this case, we only have a single CPU. So it has to steal the CPU away from this process, put it back in the waiting queue, and now the kernel itself is actually executing. So as part of that system call, right, the fork, it's going to create a brand new process that is a copy of that, but it would first be in this created state, and it would copy that process control block, copy all the memory, and all of that fun stuff, assign it a new process ID, so in this case 1338, and then it would set the parent process ID, equal to whoever called the fork, in which case it was the original browser there, right? 1337. So it would be created, in this case it's a copy, so as soon as the kernel's done copying all the data in the process control block and possibly copying all the memory now, it would go into this waiting, and then at this point the kernel is free to schedule whatever one to execute at this point, right? You have no idea which one it will do. It's up to the scheduler to decide. So say it goes back and executes the main browser. It would context switch back, go into this running code, run it for a while, and then it would context switch out and decide something else to run. In this case, right, I only have 2 processes, so it would probably just have the tab running for a while. And then after the tab runs for a while, its time with the CPU is over, goes back in this waiting queue, and again, the kernel gets to decide what to execute. In this case, it could execute, the main process again, and then go back, right? And each of these is a context switch. So eventually, the Firefox tab will be running at some point, and then it will call exit, and then go to this terminated state, and it still has a process control block empty, so the kernel is still holding on to it. It is active, and the only way to remove it is the parent process has to acknowledge its death, and we'll see how to do that today. So only at this point, it would go back to the main browser tab, it would be running, and it would have to acknowledge that that process died, and it would at least read its exit code, so whatever got returned from main or whatever was the argument to exit, and we'll see that in some examples. So in that case, as soon as it acknowledges it, the kernel can go ahead, put this back in the waiting queue, and then execute some kernel code where it would just remove it, and only now is that process dead. So it actually takes a little bit from that exit call. Another process has to acknowledge it before it's actually removed and actually dead. So then at this point, right, the Firefox browser could go ahead and execute some more. So we have some interesting questions now. Since that's the kind of normal case where the child process will exit before the parent process, and then the parent process gets to just acknowledges it, and then it can get removed. But if there's a strict parent-child relationship, right, even in the last lecture, we made sure our parent exited last by using sleep. Well, the question now is, what happens if the parent process exits first and no longer exists? So in this case, right, if this process, if the main Firefox process 1337 up there died first, and then got removed, then whose parent would this Firefox tabs be if 1337 doesn't exist anymore? Anyone hazard a guess of what you might do if you have to maintain this parent-child relationship and now the parent's no longer there? Yeah.
Maybe the child is not like the grandfather.
Yeah, so even based off this, right, it's a good analogy because we can already guess what happens when that parent, that sounds awful, when that parent dies, right? When that parent gets removed, then that process without a parent anymore would get reparented, and it would go to the grandfather, or might actually bubble up and we'll see what actually it gets reparented to, because it's actually a little bit tricky. But in general, when you're writing this, right, whenever you have forking code, you will create children if you are forking, and then the parent process is always responsible for the child, right, going off this analogy. The operating system, whenever you call exit on a process, it will just set the exit status and then store it in the process control block and won't remove it. So that process will actually still look like it's kind of active, but it'll get a special state that we'll see, right? So we can't remove the process control block. It still has some information that the parent process needs to read before the kernel can actually remove it and clean it up. And the minimum acknowledgement is, again, just reading that exit status, so whatever that return code was from the original parent, or the original child process, which now is terminated. So in this case, there's going to be two situations for the case of that child. So we kind of said the second one already, that if the parent exits first, it's called an orphan process because now its parent is no longer there, and it has to get reparented somewhere, and then someone else has to take responsibility for it. The other scenario, which is more likely that we didn't really cover before, is this zombie process. So that's what it's called when the child has exited. So it's called exit, and then no one has read that exit code yet. So for all intents and purposes, that process can no longer execute anymore. It already called exit, but it's still kind of alive, which is why it's called a zombie. So it's dead, but still somehow alive. Again, the kernel developers aren't super, they're not super imaginative. They just called it a zombie, makes sense.
It's somehow alive because the parent didn't acknowledge its death.
Yeah, so it's called exit, so someone needs to read its exit code, so it still has an entry in the kernel, and you can read that process ID. It's still active, but it can't run anymore. So it's called exit. It can't run anymore, but it's still around somewhere because we can't delete it yet. Does that make sense? Okay. So I just kind of said acknowledge without saying how to do it. And I like giving code examples and making things very, very clear. So by acknowledge, people mean this system call called wait, and it has the following API, and there's multiple different versions of it. So if you read the man pages for wait, you'll see, wait 3, wait 4, wait PID. There's a lot of calls for wait that are all, it evolved over time. So the default wait system call has the following API, takes one argument, which is the status. So it is just an address to store the wait status of a process. It's not an actual integer. So as part of the wait system call, which is why we need to understand pointers, is you give it a pointer to an integer, and it will write an integer to that pointer, and then you can read it afterwards. It's kind of a roundabout way of getting multiple return values out of a function. So its normal return value that we're all used to is just a number that represents a process ID. And if you look at the documentation, it's a C wrapper for a system call, so -1 again means there's an error, and we set that error no global variable. And then there's kind of a special case here that we'll see is it will return 0 if for non-blocking calls. So if you just want to check if there is a child that you need to acknowledge, you can just call it and have it return immediately to you. And either it will accept a child, in which case PID will be greater than 0. But if PID is equal to 0 when you make that call, it means there's still a child, it's still alive, you're still responsible for it, but it hasn't exited yet. And then the normal case is it will return greater than 0 for the child with a change, and for all intents and purposes so far, the change would be that it has exited. So the wait status also contains a bunch of information, including the exit code. So if you just try and use it straight up as an integer, it's not going to work because it only uses like the last 8 bits for the exit code and then stuffs a bunch of other information at the front. So to actually query it, they give you a bunch of macros that you should use, and we'll see that. So you can use, you can call man wait on your terminal to look at all the macros, but we'll just see the main ones you need to use. And then there's lots of different variations. We'll see later a wait PID to wait on a specific child process, or or you could also use wait PID as wait, and we'll see how to do that as well. So here is here's an example of wait. So wait by itself is a blocking call. So it will just sit there and wait and won't return until a child has died or it returns an error of some sort. So let's read this program together. So we start at main. Something created this process, so a process will be created that's running main. And then the first thing we do is we fork. So now we have 2 processes that are exactly the same, except for the return value of fork. So the child will get 0, and the parent will get something greater than 0, and that will be the process ID of the child. So again, if it returns -1, we're screwed. We just return error no, but in this case, your computer is probably dying. And then in the child, right, which is process ID 0, it will go into that if branch and just sleep for 2 seconds. Sleep is just a way to yield CPU, so it just says put this process to sleep for at least 2 seconds, and then I'll execute again after that. So the child goes to sleep for 2 seconds, and then it would go outside of that whole branch, go return 0, and then that child would just die. So the child, all it does is wait around for 2 seconds and then exits with the code 0. Then the parent, it prints f that we're going to call wait. It allocates some memory for an integer, and it just does this on the stack, right? We remember our first year C courses. So that just allocates 4 bytes on the stack, and then we can just pass its address to wait, and then it will write some bytes to that address. So after wait returns, we can check the status. Since that's the only thing we set, I just deleted the error checking, right? We would have to check if wait PID equals -1 and then there's an error. I cut that out of the slide. But then we would check if the process has exited. So we would use this macro. So wait if exited w status, so that will check whatever bit they set for that. And then if it exited, we'll say that, hey, wait actually returned for an exited process, and this was the process ID, which is the return of wait. So it'll say what process ID is now dead, and then we can just print its status. So that's its exit code, which would be that integer got returned, which is really actually just a byte. So in this case, it should, if the child just sleeps for 2 seconds and then returns 0, it should just, we should get a 0 read. So let's go ahead and look at that. So if we execute that, we call wait, and then this is the main thread, and then after 2 seconds, we see, hey, wait returned for an exited process, tells us the process ID of the child that is now dead, and its status. So any questions about that? Yeah?
I'm wondering, so when you do printf calling wait, then it will wait until the child to execute the rest of the code?
Yeah, so it'll call this, printf calling wait, which would just print that in the terminal, and then it calls wait, and the kernel will just put this process to, just block this process until that child is actually done.
How does the terminal knows you're waiting for the child is dead, not waiting for other things?
So if you look at wait, wait only waits for your child.
Only waits for the child to die?
Yeah.
Okay.
Yeah, so a process can only acknowledge its direct children, is how it works. Yeah.
How does wait work with multiple children?
Yeah, so that's a good question. How does wait work with multiple children? I'll try and come up with an example at the end, but if you read the documentation of wait, it says it will return on the first process that dies. So if you have multiple children here, say we have 2 children here, and we call wait, it will just return on whatever the first one that dies, and the order is not specified. It's just whatever dies first. So if you want to acknowledge both of them, you have to call wait twice.
Is there a way to figure out if you're waiting for all children are dead? That was great.
Yeah, so there's a way to see if all the children are dead. So we'll see a bit later in the other example, you can wait on a process ID. Oh no, that's next lecture. But you can wait on a process ID, or you can query the operating system and say, hey, do I have any children? And it will return a value for you. But in general, right, if you are the process, unless you adopt some children, which is something that sounds like it could happen, but actually to adopt children, it's kind of an opt-in system. So you only have to control the children you create. So you should know how many processes you create. Yeah.
Can you explain again why the status is 0?
So the status of 0 is because in the child, right, we go to sleep for 2 seconds, and then we return from main with 0. So it's whatever that is. So if I want to see it change, I could return, I don't know, 3 here, right? So if I go ahead and execute that, after I call wait, the child sleeps for 2 seconds, dies, returns 3, and then I can read 3. Yeah.
I'm so kind of confused how it goes into the else statement if we return 0, once it goes to the end. Like if it equals 0, then it just waits 2 seconds and then returns 0.
This?
Yeah, so like after it returns 3, how did it go to the else statement?
There's 2 processes, right? We forked at the first. Yeah. So the child would just go into the if statement because its process ID is equal to 0. It wouldn't go into the else. So it's another process that executes the else, which is the parent, which is the thing that has to call wait. Yeah.
What's the purpose of having the parent acknowledge it as opposed to just the child's exit code then terminating? Like, why do we need to acknowledge?
So you need to acknowledge it because something has to read its exit code, right? If that child just slept for 2 seconds and then said its exit code is 3, which means something catastrophic probably happened to it, and then it just gets removed completely from the kernel, no one can ever see that it had a problem, right? Someone needs to at least acknowledge it and read its error code, and that's the way the kernel checks that. At least something has at least attempted to check its error. Yep.
So waits until the child process exits, right?
Yeah.
Okay. So if you put a print statement like I don't know at the end where return 0 was, so we'd see that print statement first, right?
Like here?
Yeah.
Or
From the child.
from the child. So from the child, if you want me to print here.
No, like where you were before.
So in the else or here?
Right above the return 0.
Okay, right above the return 0 print.
So that would get printed first by the child, right?
Yes. Yeah, so if we do that, that'll get printed, well, here, I can disambiguate what they are. Because that's returned from fork, right? Okay, so they'll get executed twice, one in the child, one in the parent. But because we're waiting, the parent's waiting for the child to die, that should always get printed first because the parent's still waiting for the child to die, right? Sounds terrible, God. So don't worry, the whole waiting to die, it will get worse in the next lecture. So if we call wait,
Shouldn't child
oh, right, I have a, yeah, sorry, I put a return there. Oops. Yeah, so if I do that, then I will always get here with the child first because the parent has to call wait. So it won't go past this wait until the child's died. So it will always print here 0 before, which is from the child. And that's actually a good segue into later lectures where we have to ensure order between things. So that's one way you can ensure order between things. Yep.
So what was the status code 0 this time and 3 last time?
Oh, because I just deleted I had to return 3 here.
So you return 3, so the status code is 3?
Yep.
Isn't that dependent on the OS system? How the status code is?
No, the status code for a process is whatever number you gave to exit. So there's 2 ways to give a number to exit. You can just call exit with a number, or you can return to main with a number, and then C will put that into exit.
Oh, so you
for you.
return, then you realize there's no upper stack calls, then the child exits.
Yeah, so if I return here in the child, that's a return from main in the child, so the child will exit with the error code 3, and that's why I didn't see that print statement at the end, because the child's dead by that time. Yeah.
So if I call the wait function, what will be the state of the parent process, like block?
Sorry, if you call wait.
If I call the wait to check if the child process has died or nothing much happens, is it the parent process kind of suspended or blocked?
If you call wait in the child?
Yeah, no, I just call wait.
Yeah.
If any child died.
Yeah, so if you just call wait, the parent process will be blocked. So it's waiting for something to die. So it can't resume because it's just stuck at that wait call. So it's just waiting for something to die. Again, sounds terrible. Okay, well, so that is what you're supposed to do. Yep.
Is this the only way to establish order between the parent and the child?
So it's it's pretty much the only way to establish well, no, there's lots of ways to establish order between parent and child. This is one of it, so you can just wait until it dies.
Is this one more hard-coded? Because what if you sleep 2 seconds is not enough?
So the parent will just wait until the child, so it can sleep as long as it wants. Right. Okay, so let's get into zombies now and prove that they're actually a thing. So a zombie process is just waiting for its parent to read its exit status again. It can't be removed by the kernel because if it has an error or something at least needs to acknowledge it. So it's been terminated, so it can no longer run, but it hasn't been acknowledged, so something hasn't called wait on it. So again, process may have an error in it or something where it never reads the child's exit status, and that's up to that user program, but ideally, you would read the exit status of any processes and check that they're, by convention, non-zero, which means they have an error. So another thing that we'll see next lecture is back into the land of interrupts. So an operating system can actually interrupt a parent or process and kind of prod it to acknowledge a child. So you essentially get an interrupt that we'll see on Unix systems. They're called signals. And it'll be like, hey, a child's died, so you don't have to just wait in a blocking call. And we'll see some alternatives to that in the next one. But again, it's just a suggestion. You're free to ignore it. And that's a form of IPC. So interrupts, are a way to communicate between 2 processes. In this case, if the child dies, the kernel can, prompt your process to try and acknowledge it. But you can also send signals to processes yourself to try and get them to stop executing, which you've probably done before. Or the kernel might also just send a signal to kill something if you segfault it. But the operating system, again, has to keep track of that zombie process until it's been acknowledged. And then if the parent ignores it and it dies, right, the zombie process needs to wait to be reparented or adopted. And then you kind of have this weird situation where that process is a zombie orphan, which, woo, that terminology. But let's just check the zombie example real quick. So don't worry about that print state code. All right, so in this program, again, we're going to there's some process is going to get created that starts executing main. Then we're going to fork 2 processes. We don't know what order they'll execute in at this point, but there's now 2 of them that are clones of each other, except for the value of PID, of return PID. So again, let's ignore errors. And then in this case, the child's just going to sleep again for 2 seconds, and then would hit return 0 and then exit. So in the parent, I'm just going to sleep for 1 second, and again, the child is alive for 2 seconds. So I only wait for a second, and then I read the process's state, and you can see the code if you want this, but this basically just checks that proc file system. So it knows the process ID of the child from the fork, so you can go ahead and read its status and do whatever you want. So that's what print state does. It's just going to open, proc, whatever the number of the child is, and then kind of parse the status file there. So I have it to just print the state, and in this case, it should hopefully print the state. If there's a problem with the print state function, it returns the error number from that. Then after 2 seconds, I print the state again. And in this case, it should be a zombie because it has died now, because main takes a total of 3 seconds, right? After 1 second, it'll read it. It should be alive. Anyone want to hazard a guess as to what state the child will be in after 1 second? So, well, I guess the Linux terminology is kind of dumb. Would it be running? Would it be a zombie? Would it be sleeping? You got like, okay, well, it should be sleeping because we told the child to sleep for 2 seconds, and then we woke up after 1 second, and we're seeing what state it's in. Whoops. So if we do that, we check first state it's in is sleeping, and then we wait another 2 seconds, check its state again, and see that it is now a zombie because we haven't called wait on it yet, right? We're still, right, at this point, we're still terrible parents. All right, any questions about zombie? This is basically just showing it does exist, and it is a thing. All right, so that is a zombie. I pressed the wrong button. All right, so an orphan process, if we go the other way, an orphan process needs a new parent. So it's lost its parent process, it is no more, and the child process still needs something to acknowledge, its exit code. Well, the operating system, or in this case the kernel specifically, because it would be executing in kernel mode, need to reparent the child, and the default choice for most Unix-based operating systems is it will just reparent everything to init. So now we know the second job of init. So the init process is now responsible for acknowledging all of the orphans. So it is kind of by default, you can think of it as the orphanage. So it has 2 jobs, right? So you can actually write your own init now if you wanted. So init just has 2 jobs. Remember, when the kernel boots up, it just creates 1 process, and then that process is responsible for creating every other process, and it would just do it through fork and execing a bunch of stuff. So if you want to write your own init, you have to create every other process that's on your machine. As soon as you create one, generally they'll just kind of spiral out of control. And then you also have to kind of acknowledge all the orphan children that come to you that may or may not be orphan zombies at that point, right? And then, so if you look at the code for a very, very simple init, because you won't know the process ID of all the child since they get reparented to you. So that's why the default wait just waits for any children that comes. So if you're init, all you do is you constantly just call wait. So you can accept literally any child that comes to you. All right, so let's look at the orphan example and see where it actually gets reparented to. So in our orphan example, we'll do the same thing we always do. We will immediately fork, so now there's two processes. We will ignore error codes because that's what we like doing. Then in the child process, which is still alive, we'll just call this get PID, so get the parent's process ID. So the child just immediately prints off what its parent's process ID is, which would be the original process. Sleeps for 2 seconds, and then it prints its parent's process ID after waking up for the sleep, and then it would return 0. And then in the parent, it just sleeps for 1 second, and then it returns 0, and now it's dead. And thankfully, anyone hazard a guess of what would read the original process's error code? Or what called wait on the original process? Yeah.
Would it be the parent of that process?
Yeah, and what would the parent of that process be?
Would it depend on what the process we are? Like, could be the shell?
Yeah, so likely it's the shell. So generally, shells are written correctly, and they will, wait, and that's another thing the shell will do. So that's how it, prints off the exit number, because it waits on whatever process it spawns. But if we go ahead and run this, it will look weird. So the child's parent ID is, 3006, and then we wake up again after our parent is dead and deleted as well, because if it was still a zombie and the shell for some reason didn't read its exit code, its parent would be a zombie. So it wouldn't get reparented because it's technically kind of still alive. But in this case, our shell works as we hope, and then we see that its process ID after sleeping is 333, and by default, I said it should get reparented to init, which is, process 1, which is the great-great-great-great-grandparent of every single process on your machine. So let's figure out what process, 333 is. So we can go ahead and look at our proc file system, read the status, and let's just print off its name. So if we print off its name, it's something called systemd, which is what I told you is generally, on Linux systems at least, process ID 1. So this is system ID for your actual specific user, and it's kind of like an opt-in. So you could actually create a process that will kind of opt into the kernel to readopt everything. So, but instead of being called like an orphanage or something that sounds, I guess, more friendly, the name of something that accepts children is called a sub-reaper, because it just kills everything. I didn't name it, don't look at me. So yeah, instead of trying to go the nice one, the kernel developers decided to call it a sub-reaper, and process ID 1 is by definition the reaper, so it kills everything. So nice and friendly, right? Especially on a Monday morning? All right, any questions about wait? Yep.
With the shell, the shell, does it have a parent? Like, would that be in it, or what is the root parent?
Yeah, so the shell would have a parent. I think I showed it the last lecture, but the whole thing on Linux is generally it would look like init, and then init would probably spawn like that user system ID, and then the process under that would probably be my GUI interface here, like this thing. In this case, it would be called GNOME shell, and then in this, GNOME shell would launch Visual Studio Code. So the parent of Visual Studio Code would be GNOME shell, and then Visual Studio Code has a built-in terminal, so the terminal would be a child of Visual Studio Code, and then the shell runs within the terminal, so it would be a parent of that, and then your process would be under that. Yep.
Can a zombie be resurrected?
No. There's no resurrection in Unix land. It is dead.
So is the orphan reparented to the system D?
Yeah, so it'll get reparented to the next sub-reaper if you go up. So if you just follow the chain of parents, right, because it's unique, it'll go up until it hits a reaper. And in this case, just on this, it's systemd. If you go ahead and you have a Mac and you download the examples and you execute it, because they also work on Mac, you'll see that it gets reparented to process ID 1, which is more what you expect. So if I run this not on Linux, if I run it like directly on my Mac, it gets reparented to 1. All right, any other questions?
Can system D be killed? Then it will be reparented to, you mentioned the chain up.
Yeah. Do I want to kill it right now? All right, any other questions before I do something really stupid? And stupid, not your question, stupid to my VM, to be clear. All right, well, I guess let's see what happens. So what got reparented to was process, 333. We'll see in the next lecture how to actually send signals, but this is where the terminology gets even worse. So to send a signal to a process, you would think that it's something nice called like send signal or something. Anyone want to hazard a guess based off like our whole rampage so far, what it's probably named? Yeah. Death Note? Really close. It's called kill. So this is also why if you segfault, you'll see like killed thing because, all right, first off, I saw tons of this on Piazza. Can anyone actually tell me why a segfault happens? Yeah.
Trying to access memory that you haven't allocated.
Yeah, so if you try and access memory that you don't have access to, right? So it's unallocated stuff you shouldn't be able to touch. That's what a segfault is. And a lot of you are getting segfaults in Lab 1. So most of them that I've seen are like, so you're opening a big file, right? And then you think it's doing like C-string stuff on it. But if you just read the contents of a file, what's unique about a C-string? What does it end? What's a C-string end with? A 0, right? If you just read the contents of a file, does it end in a 0? No. So if you treat that whole file as a C-string, which just anything you do to a C-string, right? It's just going to kind of iterate over it until it hits a 0. So what do you think happens if it iterates through it until it hits a 0, but it doesn't have a 0 in it?
Access the non-allocated memory.
Yeah, so it's eventually just going to fall off the edge of it, right? And then it's going to access memory you're not allowed to access, and then it's going to segfault. And that seems to be like 99% of the posts on Piazza. So, all right. So let's get back into this fun, silly thing. So that's just an aside. So, and also the side effect of when you segfault, the kernel will send a signal to that process to kill it, and then it will get removed. So I can kill, in this case, kill-9 means, what is it? It's like just the kill. It's like uber kill. So in general, if you send signals to a process, it will have a chance to interact with it and then decide to, shut down gracefully or just ignore it. This signal, we'll see later, is like the you're dead. So it means the kernel just kills it. You don't have a choice whatsoever. So we kill -9 this, and if I do that, yeah, the virtual machine's dead. So I killed the parent of all my user stuff, right? So that was the root of all my user code where I was logged in and everything. So now I'm kicked back out to my login screen because I didn't kill, I didn't kill process ID 1, so my system's still alive. So I can log back in again, and I'm good to go. Yeah.
What if you kill process ID 1?
Oh no. Actually, let's launch code. All right. So someone wants to get out of here early. So yeah, if we kill process ID 1, so either one or two things could happen. Either if I kill process ID 1, right, that's the root of every process, that's the only thing the kernel cares about. If process ID 1 is gone, your whole thing is gone, right? Your user space is dead, that's it. So either this will kill the whole virtual machine, or the kernel will be smart enough and say, hey, you can't kill 1, dummy. You'll brick your whole computer. I'm actually not sure what it does.
You want to save everything.
Do I want to save everything? Nah, let's press enter. Ah, smart. Yeah. All right, so that's a good comment. So operation not permitted. Well, it might be permitted because root owns that. So yeah, let's sudo. Like. Kernel's smarter than, I guess the kernel's smarter than us. So you're not allowed to kill one, I'm pretty sure. It doesn't even give you an error message. Yeah, so the kernel's smart enough to prevent you from doing something that silly, right? I can try and kill one as much as I want. So obviously there's a special case in the kernel because otherwise it should just die, right? So kernel protects you from yourself a little bit, which is also why I'm still scared of doing this, but if anyone's tricked you into doing that and deleting everything, the creators of RM are smart and they detect this case and they won't let you do this anymore. I'm not going to press enter just in case because I don't want to set that up again. But that should be prevented. Yeah.
What if you pass it like a direct sig term signal?
To one?
Like a sig term.
Okay, so a sig term is less severe than that. So sig terms can be ignored. It's just a suggestion.
So which one's the real?
That -9 is the real one. So it's called kill. So it's like kill, kill, double kill, like uber dead. You're dead. Okay. Well, I guess let's wrap up then. So that's this lecture, right? You're responsible for managing processes. If you are creating processes, we should all be responsible adults here. The operating maintains that strict parent-child relationship, and you should be able to identify and also kind of prevent the following. Zombie processes, which means the child has exited first, and you need to acknowledge it by calling wait. And then you don't want to create orphan processes, but if you did, they will get reparented, likely to init. For the purposes of this course, we'll just say they get reparented to process ID 1, because that just makes things easier. And then process ID 1 would acknowledge them and then clean it up. If it didn't, right, if process ID 1 didn't clean up all of the children, the zombies would just start piling up, right? And if there's a maximum number of process IDs, which is like 32,000, as soon as you hit 32,000 zombies that aren't cleaned up, you can't launch any new processes. Yeah?
So it's more like if we don't manage our children, like, and we die first, that's not okay, but like we should. Like, we don't have to, but we should. Is that
You can. So in some situations, you might want to do that, but you should know what you're doing at that point. So, yeah, so like, let's go back a lecture real quick. So if we did this multiple fork example now that we can kind of understand, right? Multiple fork, was it? Oh, right, because I killed everything. So in the multiple fork example, where we created new processes and we never acknowledged them, but all the new processes outlasted us anyways. So all the main process did, if we remember, it just launched, in this case, 4 new processes. So all we had to do is launch 4 processes, and then all the children did something that took way longer. So in this case, we know we're going to die first. We don't really need to acknowledge all the children because we know we're going to die first. The shell will acknowledge us. So also to understand this too, then since we die, while all the children are running, they're going to get reparented to something. So then when they exit, something acknowledges them. Yeah.
So if a child process is reparented to the init process,
Yeah.
will the init process will just externally call the wait, or it has some other mechanisms?
Yeah, so the simplest init will just have an infinite loop that just calls wait.
So will that just make the init process to be kind of suspended?
Yeah, so most of the time it'll sit there just waiting for children. Because most of the time it just launches some processes and then they do some more fancy work. All right, cool. So you should be able to identify those 2 things and hopefully play around with processes now. So just remember, Pulling for you. We're all in this together.